This is Pre-Algebra, Chapter 9, Section 4. Today we're talking about real numbers. We are going to be able to compare and order real numbers by the end of this lesson. Our first vocabulary word is irrational number. An irrational number cannot be expressed as a fraction for any integers. Also, any decimal representation does not terminate or repeat. So it doesn't end and it doesn't have a pattern. Can anyone think of a very famous irrational number? Hopefully, you are able to come up with the very famous pi. Pi is a very famous irrational number. It's irrational and can be represented by the fraction 22/7. Now, this is not an exact representation in fraction form, and the decimal form is approximately 3.14, but we know this goes on forever and ever and does not repeat, and it does not end. All right, so let's talk about real numbers. Real numbers are positive, negative, large, small, decimal, fraction, whole number. They're all numbers that we use regularly, and they are not imaginary numbers. Real numbers also include both rational and irrational numbers. Rational numbers are different from irrational numbers. Rational numbers can be expressed as a fraction for any integer, and if it is in decimal form, the decimal ends or it repeats. So in example 1, let's classify real numbers. First, we want to find the decimal form of 7/10. Close your eyes and say that out loud. 7/10. Can you visualize what that decimal looks like? 0.77. What type of decimal is this? This is a terminating decimal. This decimal ends immediately. 0.7, done. It is a terminating decimal, so this is a rational number. So rational number. B, 2/9. If you can't figure out 2/9 in your head, you can put it in the calculator, and we get 0.22222 and forever and ever. We are just going to keep writing 0.22222. So we are going to shorten this a bit to 0.2 with the repeating line on top. You got to put that line on top to show that this decimal repeats forever and ever and ever. So this is definitely not a terminating decimal, but it is a repeating decimal. And repeating decimals are still rational. Now the last one we are going to do in this example is radical 5. Radical 5 you're going to have to put in a calculator. Radical 5. What we get for radical 5 when we put it in the calculator is 2.23606797775. My calculator ends at 5. I don't know where yours is going to end, but I don't see any patterns in this decimal, and I don't see it ending anytime soon. So this is a non-terminating, meaning it doesn't end, non-terminating, non-repeating decimal. Non-terminating, non-repeating. It doesn't end, and there are no patterns. So this is 100% irrational. This is an irrational number. Example 2, comparing real numbers. So we're just going to compare numbers and approximate their location on a number line, and then use our inequality symbols to show how they are related. So we need to graph radical 3. Well, let's plug radical 3 in the calculator and see what radical 3 comes up as in decimal form. Radical 3, I'll write it right up here. Radical 3 is 1.732205080757, and it's going to keep going on forever and ever. That's not really reasonable for me to put on my number line, so I'm going to shorten that a bit to approximately 1.7. 6 over 5 comes out to exactly 1.2. So we can see that radical 3 is irrational, but 6 over 5 is rational. Now let's look for a spot for these numbers on the number line. So we're at 1, and then we have 2. So where are we going to put approximately 1.7 on this number line? What I did here on this number line was first I found the halfway mark between 1 and 2. So I found right here, I found 1.5. And then I broke everything up so that I was working in tenths. So now it's going to be easier to find approximately 1.7 and 1.2. So if I'm working in tenths, this is 1.1, 1.2, 1.3, 1.4, the middle, 1.5, 1.6, and 1.7. So 1.7 is going to be right here, approximately, because this is definitely not exactly 1.7. And this, we need to label it as radical 3. Now, we are going to find 1.2. 1, 1.1, 1.2. 1.2 is right here, and that we will label 6 over 5. Now we need to determine which side these numbers are on. So let's see. Radical 3 is to the what of 6.5? Radical 3 is to the right. Radical 3 is to the right of 6 over 5. So that means radical 3 is closer to 2 than 6 over 5 is. So radical 3 is greater than 6 over 5. Radical 3 is greater than 6 over 5. Example 3 is very similar to what we just did, except now we have a few more numbers. So instead of using greater than, less than, or equal to determine the relationships, we're going to put them in order from least to greatest. So the first thing we want to do is figure out what these numbers are in decimal form. Decimal form is probably the easiest way to go for you. Then we're going to put them on the number line so we can read them in order. So let's find the decimal values. Okay, here we go. Radical 6 over 2 is irrational. It is approximately 1.22, but that decimal went on forever and ever. And actually, I'm going to bring it to the tenths place. So approximately 1.2. Negative 2.2 is already in decimal form, so we're going to keep that as negative 2.2. 5 over 2 is exactly 2.5, or 2.5. And radical 2 times, or negative 2 times radical 2 is approximately negative 2.8. This was irrational. I rounded to the tenths place. Now let's graph these numbers on the number line. Approximately 1.2. So we're going to go to 1, and I labeled the halves. So right here in this blue line is 1.5. So we know 1.2 is a little bit less than 1.25, so we're going to do it approximately right there, and we're going to label this radical 6 over 2. Now we have negative 2.2, negative 2, here's negative 2.5, so we know negative 2.2 is going to be about right here. Label that negative 2.2. 2.5, we're back in the positives. That goes exactly on this line, halfway between 2 and 3. So that is 5 over 2. And the last one, negative 2.8. This is 2.5. This is about negative 2.8. And we're going to label that one negative 2, radical 2. And that goes right there. So now that these numbers are on the number line, we can see which order they go in. So we are going to label them or write them in a list from least to greatest. So negative to positive. And there you have it. Our numbers in order from least to greatest. 2 of them are irrational and 2 of them are rational. But they all can be found on a number line. Here are your 4 checkpoint problems. I would like you to plug these into the calculator and tell me whether or not they're rational. And then these 2, you are going to determine which of these numbers is greater. Pause, come back when you're finished. Here are your solutions. Number 1, 8 over 11, this was a repeating decimal, so it is rational. Number 2, radical 7 was a non-repeating, non-terminating decimal, which would make it irrational. Number 3, square root of 49 is 7. That is a whole number and rational. And number 4, radical 2/5, that is a non-repeating, non-terminating decimal, which makes it irrational. Number 5, negative 3 over 2 came out to negative 1.5. Negative radical 3 came out to approximately negative 1.7. Negative 1.5 is closer to 0 than negative 1.7, so negative 3 over 2 is greater than negative radical 3. And number 6, radical 10 is approximately 3.2, but irrational, and 3.5 is 3.5. So 3.2 is less than 3.5. Radical 10 is less than 3.5. Let's move on. Here's 2 more checkpoint problems. Using a number line to put these numbers in order from greatest to least. You're going to use the same method. Pause and come back when you're finished. Alright, here are the answers to your second set of checkpoint problems. First, we had to put them all in decimal form so we can plot them on the number line. Once plotted on the number line, you're able to see the order from least to greatest. Some of your numbers are very close together, so we had to extend out into the hundredths place to be a little bit more accurate with those irrational numbers. So even though they're only slightly larger or slightly smaller, there's still a specific order that these numbers will go in. So here are your answers. And let's move down to example 4. Example 4 is using irrational numbers in a real-life situation. So after a car accident, the police officer finds the length of the car's skid marks, and they are 98 feet. So the car's speed is unknown, but we are going to use this expression and the car's skid mark length to find the car's speed to the nearest tenth of a mile per hour. And this is real life. Police officers and investigators use a car's skid marks to determine how fast they were going, to determine whether or not they'll get a ticket if there was an accident that they weren't there to witness. So we have speed equals radical 27 times L. L being the length of the skid marks. So we are going to use substitution and substitute 98 for L. Now, inside the radical, we have to multiply 27 and 98. When we do that, we get radical 2,646. And because this is a real-life approximation, we are going to plug that number into the calculator and get a decimal approximation. So our answer is approximately 51.4. So that means this car was traveling 51.4 miles per hour. Now, if this was a 35, they were traveling 51.4 and a 35, they're definitely getting a ticket.